Trilogy Physics Paper 2, Higher. First question. A teacher demonstrated how the frequency of a wave on a string affects the wavelength of the wave. This is the setup that they use. Here is a signal generator, and that signal generator produces a frequency which goes to the vibration generator. The vibration generator moves up and down, and that causes the string to move up and down. The wooden bridge that is movable is used to adjust the string so that a full wavelength is shown. The string is taut, that means it's pulled tight using the masses on the other side. It asks you to describe a method the teacher could use to investigate how the frequency of the wave affects the wavelength. Now remember, you move the wooden bridge and you measure the wavelength on the ruler. So the first thing we can do is use the signal generator to adjust frequency. You can keep the number of waves the same, keep the number of waves on the string the same. How do you do that? Move the wooden bridge. You observe a stationary wave. What is a stationary wave? It's a wave that if you were to look at this wave that's shown in the picture, what you would see is almost as if it's like flickering. You won't see the wave move across. It will be flickering because the wavelength shown, the amount of string used is the wavelength all the time. Then measure wavelength using ruler or the meter rule on the table. Repeat for different frequencies to produce different stationary waves. Fantastic. Use the physics equation sheet to answer the questions 1.2 and 1.3. Which equation links frequency, wavelength, and speed? V equals F lambda. That's the equation. Wave speed equals frequency times wavelength. The wave on the string has a frequency of 45 Hz. The wave speed is 35.1 meters per second. Calculate the wavelength. First of all, you identify the data from the question. You choose a formula, which we've already done, and then you convert if necessary, but substitute the numbers into the formula. So 35.1 is actually equal to wavelength frequency 45 times by wavelength. Therefore, wavelength is equal to 35.1 divided by 45. The answer happens to be 0.78 meters. Superb. Figure 2 shows an Olympic gymnast performing a floor routine. The floor contains springs. The gymnast lands on the floor. The force compresses the springs on the floor. When the spring is compressed, elastic potential energy of the spring increases. Explain why compressing springs on the floor helps the gymnast jump high. So when the gymnast compresses the springs on the floor, elastic potential energy is stored. When the spring decompresses, the elastic potential energy, maybe I should put elastic potential energy of spring decreases and the kinetic energy of gymnast increases. So, and this helps gymnast jump higher. The spring does work on the gymnast. Superb. Next question. When the gymnast lands on the floor, one of the springs compresses by 1.2 centimeters. Spring constant is equal to 8,500 newtons per meter. Calculate the elastic potential energy of the spring using the physics equation sheet. So the first thing is find the data. Here it is. That's compression. We can call it extension also. However, it's in centimeters. It needs to be converted. To meters. How do I convert from centimeters to meters? Well, there are 100 centimeters in 1 meter. So to go from centimeters to meters, I have to divide by 100, and which is 0.012 meters. I'm just going to underline that. That's one part of my data. My spring constant is another thing, and I have to calculate the elastic potential energy. That's what I'm asked to calculate. Elastic potential energy is equal to half times K times E squared. Well, what's K? This is K. Okay, that's a spring constant. Remember, extension has to be squared. So half is 0.5 times by 8,500 times by 0.012 all squared gives me elastic potential energy, which happens to be 0.612. Now, 0.612, the final thing to do is add the units. Energy as the units joules. Superb. Joules. Okay? So here a student investigated a spring with a different spring constant. When the masses are placed on the spring, it compresses. The student measured the compression of the spring for 4 different masses. Describe how the compression of the spring could be determined. One way to do it is measure original length and new length. New length meaning the length after the mass is added on. So compression equals original take away new. That's it. The other way you could do it is remember the equation F equals K times E. So if you know the spring constant and you know the force of the masses, you'll be able to work out the extension. Explain why the investigation should be done on a laboratory floor rather than on a table. Those look like very heavy masses because masses could fall off the table and cause injury. That's it. That's the only reason. The spring constant is the gradient of a line best fit shown on figure 4. Determine the value of delta y. That means change in y. It's already labeled here from here to here. That is 80. Well, how do I know it's 80? Because I've got the mark scheme here, but also because there are 10 squares in between 0 and 100. So this has to be 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, So it goes up in tens for each tiny square. That's 80. So that's 310, 320, 330. 330 minus 80 gives me 250 newtons. Determine the value of delta x. Well, what does it go up in now? It's 0.1, then 0.01 and 0.02. So there's 0.011, 0.012, 13, 14, 15, 16, 17, 18. Yeah, so it goes up in 0.001s. Therefore, this is 0.01 and this is 0.052. 0.052 take away 0.01 gives you an answer of 0.042. Determine the spring constant of the spring. Spring constant we decided was change in y divided by change in x. K is equal to delta y over delta x, which is equal to 250 over 0.042, gives us an answer of 5,950 Newton meters. The units are already given for you. Question number 3. This question is about electromagnetic waves. Electromagnetic waves are grouped according to their wavelength and frequency. Electromagnetic waves are transverse waves and can travel through a vacuum. Give one other property that is the same for all types of electromagnetic waves. They can travel through a vacuum and they're all got the same frequency. They can travel through a vacuum. They're grouped by their wavelength and frequency. They all have the same speed. Okay, so the speed of all EM waves are the same, which is 3 times 10 to the 8 meters per second. Okay, so speed of light. What is meant by a transverse wave? Longitudinal means along the direction of the wave. The vibrations are along the direction of the wave. Transverse waves means the vibrations or the oscillations, which means vibrations, are perpendicular to the direction of energy transfer. You have to remember it like this. In a transverse wave, the oscillations are perpendicular to the direction of the energy transfer. Here's the wave. The energy is being transferred in the direction that I've shown, and the wave moves up and down like that. Which group of electromagnetic waves is used for satellite communications? Microwaves. That's what your phones use. Visible light is the only group of electromagnetic waves that a human eye can detect. Which color of visible light has the shortest wavelength? Remember, it goes red, orange, yellow, green, blue, indigo, violet, and this is long wavelength, this is short wavelength, so violet. The three highest frequency groups of electromagnetic waves are hazardous. Describe the risk linked to each group of high frequency electromagnetic wave. Last question, we did the shortest wavelength visible wave, which was violet, and short wavelength means high frequency. Anything above violet on the electromagnetic spectrum is higher frequency than violet. So the next thing up from violet is ultraviolet. Then the next group is X-rays, and the next group is gamma rays. Now, some of the risks included is skin damage, cancer / DNA damage, and then sunburn, you could say. That's it. The electromagnetic waves emitted by a mobile phone and send the information to the laptop. The electromagnetic waves emitted by the mobile phone have a period of 4 times 10 to the minus 10 seconds calculate the frequency of the waves. This period is talking about time period, which is how long a wave takes, one wave takes to pass. Calculate the frequency of the wave, use the physics equation sheet. From the physics equation sheet, we know that time period is 1 divided by frequency. So 4 times 10 to the minus 10 is equal to 1 over frequency. Therefore, to calculate frequency, you do 1 divided by 4 times 10 to the minus 10, which gives us an answer of 2.5 times 10 to the power of 9 hertz, because frequency is measured in hertz. That's the answer that you put here. The electromagnetic waves are produced by oscillations in the transmitter of the mobile phone. Explain how the oscillations in the transmitter enable information to be transferred to the detector in the laptop. So you have a device that has a transmitter, which means it has an alternating current producing a electromagnetic wave, and this electromagnetic wave is absorbed by the detector, and the detector, in the detector, it ends up having an alternating current which is with the same frequency. So here's the transmitter, here's the detector. What wave is used? Either radio waves or microwaves are used for communication between devices. So I'm going to say radio waves are produced by the transmitter. The detector absorbs the waves or the energy, and this produces an alternating current with the same frequency as the waves. Okay. Figure 6 shows two magnets and a wire. There is a current in the wire. A force acts on the wire in figure 6. What is the direction of the force of the wire? Remember, you are using Fleming's left-hand rule. So the thumb is for motion, the forefinger is for field, and the middle finger is for current. So the field is from right to left, and the current is from us to away from us, then the force will be acting down into the page. Next, the length of the wire in the magnetic field between the magnets is 80 millimeters. The current of the wire is 4.6 amps. The force on the wire is 0.092 newtons. Force, current, and length. Alright, use the physics equation sheet and calculate the flux density between the magnets. So the equation that we want is F equals BIL, force equals flux density times by current times by length. And then what we do is we have to convert the length first, because it always has to be in meters. To go from millimeters to meters, there is 1000 millimeters equals 1 meter, so you have to divide by 1000 to go that way, and so you divide 80 by 1000 and you get 0.08 meters, and then you substitute all your numbers into the equation. 0.092 is equal to B times by 4.6 times by 0.08, which gives us B, well, after rearranging, is 0.092 divided by 4.6 times 0.08. Remember, I'm having to do this this step and this step, even though you could skip these steps, because those steps give you the marks. Okay, and finally the answer happens to be 0.2 and 0.25 Teslas. This is the one unit that is like really easy to remember. Magnetic flux density is Tesla, like Elon Musk. Now, figure 7 shows the electromagnet close to a permanent magnet. The electromagnet exerts a force on the permanent magnet. The permanent magnet exerts an equal and opposite force on the electromagnet. Which law is this an example of? This is a forces question disguised as a electromagnetism question. The example where equal and opposite forces are exerted is Newton's third law. Next question. Give two changes to the electromagnet that would increase the force exerted on the permanent magnet. That is asking, this is back to an electromagnetic question, magnets question. This is asking, how do I increase the strength of the electromagnet? One is more coils of wire. Number two is more current in the wire. Okay, so more coils, more current. You could add bring closer. That would also increase the force. Give two changes to the electromagnet that would reverse the direction of the force exerted on the permanent magnet. Reverse current. Okay, if you reverse the current, the north and the south side flip over, or you could wrap coil in reverse, or you could take this electromagnet and just flip it around. Okay, all those three things will get the desired change. So question 5, a safety test was carried out to determine how the speed of the car affects the stopping distance of the car. At the start of the test, the car was moving slowly, the car accelerated. That's my acceleration at 5.8 meters per second for 2.5 seconds. That's my time taken. The final velocity of the car was 20 meters per second. That's my final velocity. Calculate the initial velocity of the car. We call that u. Now, use the physics equation sheet. We need to find a equation that links acceleration, change in velocity, and time. So acceleration is equal to change in velocity divided by time taken. Change in velocity is equal to final velocity minus initial velocity. So we can use that at a later time. So 5.8 is equal to change in velocity divided by 2.5, which gives us an answer of final change in velocity being 5.8 times by 2.5, which is 14.5 meters per second. Now, change in velocity, 14.5, is equal to final velocity, which is 20, minus initial velocity. Therefore, initial velocity is 20 minus 14.5, which gives us 5.5 meters per second. And that's what we write here. The reaction time of the driver was measured. How can the reaction time of the driver be used to calculate the thinking distance? Reaction time, what you can do is you can multiply the speed of the car by the reaction time. That will get you how far the car will travel while he is thinking. So you say multiply the speed of car by the reaction time. The car was driven at a constant speed. The driver applied a maximum braking force and the braking distance was measured. The test was repeated and this is the curve that's produced, braking distance and speed. Now, you're asked, how is braking distance and speed related? This shows inverse relationship and that's the graph produced. This shows direct proportionality and that is the graph produced. This shows proportionality but to the square of speed. So the x squared graph looks like this, and that's what we get. So this is the correct answer. During one of the tests, the brakes were applied with a force of 6,250 newtons, and the deceleration of the car was 5 meters per second. Now, this is force. Deceleration doesn't really have a letter, so we just use acceleration. And then the braking distance of the car was 14.4 meters. This can be distance or D or S. I'm just going to use S for now because that's more applicable. Determine the momentum of the car before the brakes were applied. This is a multi-step question, that's why it's worth 6 marks. Momentum has the equation P, P is equal to mass times velocity. That's the equation for momentum. We're missing mass. How do I find mass? Using the numbers given. Well, there is an equation that links force, mass, and acceleration together. Force equals mass times acceleration, which means 6,250 is equal to mass times by 5. To produce 5 meters per squared acceleration on a given mass, 6,250 newtons of force have to be used. Therefore, mass is equal to 6,250 divided by 5, which gives you an answer of 1,250 kilograms. Okay, so that is my mass. I'm just going to keep that there. Then we need our velocity to find momentum. We don't know our velocity, however there is a clue to tell us our velocity. It says the braking distance of the car was 14.4 meters. Well, we have a relationship between speed, or velocity in this case, and the braking distance. So if the braking distance of the car was 14.4 is here, then we know that to produce that braking distance, this is going to be really annoying for me because I'm not going to get it straight. To produce that braking distance, the velocity or the speed has to be 12 meters per second. So V equals 12 meters per second. Just for the people who are confused, how I did that was I knew I needed to have a speed or a velocity. Speed and velocity are similar, and to find velocity or speed, I needed to look where speed can be related to the braking distance because the braking distance is given. And so what I did was I looked at the braking distance here and I found the speed here. Okay, now I've got my velocity, I've got my mass. So P is equal to M times V. 1,250 times by 12 gives us an answer of 15,000 kilogram per meters second. Kilogram meters per second. Last question. Rockets have been developed so that people who are not trained astronauts can pay to travel to space. Figure 9 shows the passenger module of the propulsion module of a rocket. The propulsion module burns a large volume of fuel. The rocket was initially stationary on the ground. The rocket accelerated upwards until it reached a height of 40 kilometers. That's a distance, however it's in kilometers and it needs to be in meters. Kilometers, 1 kilometer is equal to 1,000 meters, so it's 40,000 meters. The constant acceleration of the rocket was that much. That's my acceleration. Calculate the velocity of the rocket at a height of 40 kilometers. So we need something that links acceleration, distance, and velocity. So the equation is v squared is equal to u squared plus 2as. This equation links velocity, acceleration, and distance with initial velocity. However, that is 0 because it was initially stationary. So v squared is equal to 2 times 6.48 times by 40,000. Therefore, v is equal to the square root of 2 times 6.48 times 40,000. Therefore, V is equal to 720 meters per second. Explain how the weight of the rocket changed as it accelerated upwards. Now, as it accelerated upwards, weight decreased. Why? Two reasons. While at 40,000 kilometers, 40,000 meters in the above the ground, you'll have less gravity, but you also have less fuel as the fuel is used up, and less gravitational field strength. So for both of those reasons, the weight decreased. At the height of 40 kilometers, the rocket stopped burning fuel, and the rocket continued upwards to its maximum height of 60 kilometers. So here's a rocket, it's continuing to move upwards. The thrusters sort of have broken off. Explain why the velocity of the rocket decreased between 40 kilometers and 60 kilometers. Why did it slow down? To slow something down, the resultant force has to act opposite to the direction of motion. So resultant force acts opposite to the direction of motion. What's the opposite to the direction of motion? It is down. So that's the resultant force. Okay? Acts down. Why? Because of gravity, or the weight and drag from air resistance. Acts opposite, and there is no force pushing it forward, so no force to counteract it. So you have a resultant force towards the earth. So resultant forces towards the earth, weight and drag acts opposite to motion, and no force to counteract this. So at the height of 60 kilometers, the two modules of the rocket are separated, and the passenger module fell back to the earth, and it's being slowed down by the parachutes. Parachutes cause the passenger module to fall with a lower terminal velocity than if the parachutes were not used. Explain why the parachutes allow the passenger module to fall with a lower terminal velocity. This is a tricky question in my opinion. It's asking for the second stage of the parachute diver question. The second stage is, in the first stage, it reaches a terminal velocity. So if it was just this on its own, it will have reached a terminal velocity. And then with the parachutes, it will have reached a new terminal velocity. Okay? At this new terminal velocity, the air resistance is equal to the weight. So air resistance equals weight at new speed. Okay, which is a lower speed. So what you have to say is, if this is the same, the resultant force equals 0. Okay, so parachutes increase the area, so there is the same air resistance at a lower speed, so the resultant force at a lower speed with the parachute open is 0. Now, this question is tricky because you would be initially sort of thinking to yourself, I should just say the parachutes make the air resistance more, therefore it slows down. Yes, because it slows down, the air resistance also decreases and it balances out with the weight, and therefore it's a new terminal velocity. That's why it's a new terminal velocity. Well done. Thank you.